Having the formula for the PDF little f of x is great because we can see the shape of the distribution, we can see approximately what the more likely types of values are, the less likely types of values are, and having the formula for the CDF, capital F, is fantastic as well because it allows us to streamline our probability calculations and it allows us to answer questions about percentiles or quantiles of the distribution as well. But what if we just wanted to summarize this distribution with one or two numbers? What if we wanted to answer the question, well, what's a typical value that we might observe from this distribution? And what's the give or take associated with that? Usually when I like to summarize distributions, I say the typical value from this distribution is blank, give or take blank or so. So how do we fill in those two blanks? Well, we're going to discuss the expected value of a continuous random variable and the standard deviation of a continuous random variable as well. Much like what we did back in discrete world, the formulas are going to look pretty much the same. Instead of doing summation notation, we're just going to be using integral notation instead. So how do we get that average value of a continuous random variable, the expected value? Well, we're going to do something similar to what we did in discrete world. So to get that expected value from a discrete probability distribution, what we did is take a weighted sum of all of the possible values, with the weights equal to the probabilities of observing those values. So we're going to do the same thing with a continuous random variable, just replacing the sum with an integral, because now we have a continuum of possible values. And so it's like we're taking a weighted sum of all the possible values of x. We're going to integrate over all the possible values of x. And what we're going to do is essentially give each value of x a weight, whatever that value of little f of x was. That's relative frequency of observing a value close to that. So by definition, the expected value is the integral over all possible values of x of just the quantity x times our formula for the PDF, little f of x. Now, just like what we did in discrete world, we're going to denote this expected value of the function, this average value of the function by the Greek letter mu. That's just a convention among statisticians and people that study probability. So relatively straightforward to figure out what this average value is, and we can interpret it as saying that this is just a typical value that we might observe. If we had to summarize this distribution with one number, the typical value seems like a smart way to go about doing it, and so we'll do it that way. Now, visually, what does the expected value of a probability distribution refer to? Well, if we imagine the shape of that probability distribution kind of carved out of wood, it turns out the expected value of that probability distribution would be where we could balance that piece of wood if we were to put it on to, say, our finger. So, for example, if I had a banana that was giving me the shape of my probability distribution, the expected value of this distribution, the average value, would be essentially where I need to place my finger so that it balances just right without tipping over. So there we go. The average value works to be right at about the center of this banana, kind of where it peaks. Makes a lot of sense. If I had kind of a funky shaped distribution, let's say like this adorable Frenchie figurine, well, all I got to figure out is where is this Frenchie going to perfectly balance on my fingers? And it's going left and right. This one's a little bit difficult to find out. But in general, I'm not going to break this thing. I'm not going to try to find it. There we go. Balance. Ta-da. In general, the expected value of a probability distribution is just where it would balance if we placed it, say, on a fulcrum. So we can think of the expected value of the function mu as something like the center of mass of the distribution, a good way to summarize a typical value. So let's do an example. We've talked about the bimodal demand probability distribution example, which might not really be the most appropriate to summarize with a single number because we have two modes. We'd probably summarize this distribution with two values. We're likely to get a value near 0.5, 0.75 or so that first peak, and 2.5 that second peak. But let's just illustrate the process of finding that expected value in R or Wolfram Alpha. So in R, not too bad. We just have to head over to it, and I've already transcribed our function. I'm going to make sure that it integrates to 1 so that I'm dealing with a valid PDF, and so I am. How do we get the expected value out? Well, it's this easy. After you've transcribed your function for the PDF, you verified its value to make any typos, so it's integrating to 1. All you have to do is preface that formula for the PDF by an x times, and that's going to be our formula. We're integrating x times our formula for the PDF over all possible values of x. And so we find that mu for this probability distribution, the expected value is right at about 2.24. If we wanted to do this in Wolfram Alpha, well, we can do that too. What I'm going to do is I'm going to transcribe my formula for the PDF, and I'm going to integrate my PDF from x equal to 0 to 3.5. In general, we integrate over all possible values of x. We start out with this just to make sure that it integrates to 1. We have a valid formula. We didn't make any typos. And once we have that, very easy to get the expected value. The expected value is just the integral of x times this equation. So we can just say integrate x times our equation to get it. And so we're going to come out with that same value of 2.24. Now, once again, is that a useful summary in this case, saying that the typical value we might see is around 2.4? Well, not really, because it's a bimodal distribution. We should really save average values, typical values for just ones with a single mode, but at least illustrates the procedure. So another example, let's model the fraction of purchases made by the upper class that would be considered luxury purchases. So capital X, that's the name of our random variable. Little x are possible values that this variable can take. In this case, anywhere between 0 and 1, from 0% up to 100%. And so if we're going to use as our probability model the function 3 times 1 minus x squared divided by 2, well, having that formula for the PDF is fantastic because we can make a plot of it, like in Wolfram Alpha, that lets us see the shape. So the most likely values are values that are relatively close to 0. It tapers off pretty quickly, going up to 100%. But maybe we'd like to summarize this distribution with a typical value. What on average do we see? All right, well, once we've verified that we're dealing with a valid formula for a PDF, if we integrate our formula over the range of possible values of x that we might see, it should always integrate to 1. We always start out with this to make sure that we didn't do any typos. Once we've verified that this does integrate to 1, well, all we have to do is take our formula for the PDF and preface it with an x times to get that expected value. So we see that it integrates to 1, so all we have to do to get the expected value is to preface our equation for the PDF with an x times. Take the integral of x times little f of x over the range of possible values of x we might see, and we find that the average value in this case is 0.375. So using this probability model, typically we expect to see a value of around 37.5%, 0.375 or so, and so we've been able to capture the variation between 0 and 1 with that single number, mu, the expected value. Now, how could we do this in R efficiently? Well, let's do it. What I like to do is to first start out by making sure that I don't have any typos. And so if I say function x, and then take my equation for the PDF and just transcribe it, which is going to be 3 times 1 minus x squared divided by 2, having a lower equal to 0 and an upper equal to 1, allows me to very quickly verify that I didn't make any typos. It integrates to 1. And here's how easy it is, once we verify this, to get that expected value. All we have to do is take our equation for the PDF and just start it out with an x times. So x times our equation is going to give us that expected value. So summarizing the probability distribution with a single value, the typical value or average value mu, isn't too bad to do. We still have to do some calculus, but Wolfram Alpha or R will be there to help us out. And so the next question we might want to ask is, okay, well, that's cool. I like knowing what the average value of that random variable is. But what if I'm more interested in the average value of some function of that random variable? Maybe I have a probability model for the amount of steel that some factory can produce, but what I'd like to know is what the expected value of that steel being produced is. So can we translate from amount to some value, where there might be an equation that tells us how much a particular amount is worth? So how would I get the expected value of that function? Well, similar to what we did in the discrete case, we're going to take our function of interest, g of x, we'll multiply that by our formula for the PDF, f of x, and then just integrate over the range of possible values that we might see. So in effect, it's kind of like taking a weighted sum of those function values with the weights equaling to the probabilities of observing that value of x that lurk behind that function. But because we have a continuum of values, the sum is now an integral, and so we need to do a bit of calculus. So for example, that steel example. So x, capital X, is our random variable that describes the amount of steel that's being produced by a certain factory using a certain recipe. And we have an equation that tells us what the worth of that steel is. So maybe 2 times the log of x plus 1. And so we'd like to figure out, well, what's the expected worth? We might have a probability model for the amount produced. What's the expected worth of that amount that ends up getting produced? So let's go through the example. Let's imagine that our probability model that describes the amount of steel produced looks like this. Our formula for the PDF, little f, is 1 over 5 times the quantity x over 10 plus 1 to the third power. Obviously, values of x that are at least 0 are the only ones that are going to be allowed. And so using this probability model, well, let's go and figure out, well, what's the expected worth? All we have to do is take our equation that translates a particular value of x, the amount that's produced, to the worth of that, in this case 2 times log of x plus 1, multiply that by our equation of the PDF, and integrate over the range. All right, so let's do this work in Wolfram Alpha. So first, let's actually look to see what the probability distribution is for the amount of steel that's being produced. Here's my equation for the PDF, and here's Wolfram Alpha's visual. So we can see that larger values are progressively less likely according to this probability model. Let's verify that it's a valid probability model by integrating from the smallest possible value up to the largest possible value, which I've left open-ended, so technically infinity in this case. It integrates to 1, so great. I got a valid PDF. If I want to know the expected value of the worth of that steel, and the worth of that steel is just 2 times the log of x plus 1, all I have to do is transcribe that function of interest, multiply it by my formula for the PDF, and take the integral over the range of possible values of x that I might observe from 0 to infinity. So in this case, I get a value for the expected worth of about 3.46. So how would I do this in R? Well, first I want to verify that I didn't make any typos with my formula for the PDF, so I'd integrate my function for the PDF over the range of possible values. So in this case, from 0 up to capital INF, infinity, and I verify that it integrates to 1. It's a valid formula for a PDF. And so to get the expected value of the worth, well, I just preface that function with the formula translating what a value of x is in terms of worth, 2 times log of 1 plus x, that function of interest. And so once I run that through, I find that the expected worth of the steel that's being produced is 3.46. Now, being comfortable with this procedure for calculating the average value of a function is of paramount importance, especially in business analytics, because we've discussed that when it comes to probabilistic modeling, using averages just really isn't good enough if we want to summarize a complex process. So a function of a random variable or a process with 2 or more random components that interact. And let's really hit that home by doing the calculation for the expected worth the wrong way, something that we would be tempted to do if we didn't know any better. So what do I mean by that? Well, let's go ahead and just calculate what the expected value of the amount of steel is that's being produced. So once again, I have my formula for the PDF, verifying that it integrates to 1. The expected amount of steel that's being produced is just the integral of x times my PDF. So it looks like, on average, 10 units of steel get produced. And if I were to straight up plug in that average value of 10 into my equation that relates it to the worth, I would get that the expected value of the worth, calculated the wrong way, is about 4.795. So notice how different this value is than if we had calculated the expected worth the correct way, taking our equation that translates a value of x to its worth, doing the integral the correct way. We would vastly overestimate the worth of the steel that's being produced if we had just plugged in the average value of the amount into our equation that translates amount to worth. We really have to go through our procedure for calculating the expected value of a function if we do want to characterize a more complex process. So averages aren't good enough. We really have to be careful when trying to summarize the expected value of a complex process. We've really got to do this integration correctly. All right, so along with the typical value that we might observe from a probability distribution, the average value, we'd also like to talk about, well, how far off might the values be that we observe from this distribution from this typical value? What's that give or take amount? So we might want to know, okay, the average amount of steel that's being produced is 10, but give or take how much? Give or take 1? Give or take 5? What is the standard deviation associated with this random variable? And so we're going to calculate standard deviations of random variables of continuous quantities in a very similar way as what we did back in discrete world. Instead of sums, we're going to have integrals. So how do we do this? Well, we're actually going to start out by calculating the variance of the random variable, and we'll denote that by sigma squared because it's a bit easier to get to mathematically. And the variance of a random variable is just the expected value of a very particular function. What is that function? Well, it's the squared difference between the values of x and the average value of x mu. So our equation for the variance is nothing more than the expected value of x minus mu squared, that function. So to get that, I just take x minus mu squared, multiply it by my formula, little f, my PDF, and then take the integral over the possible values of x that I might observe. And then the standard deviation, all I have to do is take the square root of that variance. My universal symbol for standard deviation in statistics is sigma, and that's really what I'm going to be after. That sigma gives me the give or take that's associated with that expected value. And so once I have mu and sigma, I can summarize that distribution by saying a typical value we might see from that distribution is mu, give or take sigma or so. All right, so once again, it's a good time to contrast the mean and the standard deviation of a probability distribution with the mean and the standard deviation of data values that we've collected. So if you've collected data, and let's say you've stored it in a vector x, well, you can get the average of that data vector by saying mean of x, and the standard deviation of that data vector with SD of x. And we can say that, okay, once we have the mean and standard deviation, the observed values are typically the mean of x, give or take the standard deviation of x or so. So when x is a vector of data values, mean and SD get you there. But if we're dealing with x being a random variable and little x's being the possible values we might see, we have to go through the calculus to figure out what the mean and standard deviation is. But the interpretation is actually pretty close. So once we have mu, the average value, sigma, the standard deviation, we can say that a typical value we might observe from the PDF is about mu, give or take sigma or so. A few different ways you can go about interpreting it, but it does help to summarize the distribution with a single value, give or take something. So let's do some example calculations of the standard deviation. So going back to the example where our random variable capital X is the fraction of purchases of the upper class that we would consider to be luxury purchases, we have our formula for the PDF little f as just 3 times 1 minus x squared over 2, valid values of x between 0 and 1. So to get the standard deviation, we actually have to get mu first, the expected value that's used in our formula. And so what we do is to integrate over our formula for the PDF little f times x over the range of values that we might observe. So from x equal to 0 to 1, and we get out that the average value is 3/8, that 0.375 that we saw in a previous example. All right, so on average, the fraction of luxury purchases is 0.375, but when we go and actually start looking at actual values, how far off from the average do we expect these to be? What is the typical difference between the actual values and their overall average? All right, well, what we'll do is calculate the expected value of the function x minus mu quantity squared. So we'll take the integral of our formula for the PDF little f, we'll multiply that formula by x minus mu quantity squared, and then throw that into R or Wolfram Alpha. So once we've done that integration, we get the variance out, sigma squared, 0.059375 in this case. We immediately take the square root to get that standard deviation sigma, and it works out to be about 0.24. So now we can nicely summarize that distribution by saying typically the upper class spends about 37.5% of purchases on luxury purchases, give or take maybe 0.24 or so, 24.4 percentage points or so. So if you really dive into the mathematics behind, hey, what does that formula for the variance of a random variable really do? If you go through the math, you can actually write out the formula for the variance of a random variable in a slightly different way that sometimes makes it more convenient to find mathematically. But for us, since we're doing this in R or in Wolfram Alpha, taking that expected value of the function x minus mu squared is definitely the way to go. But technically, what you could do is get the expected value of x squared. So take the integral of x squared times your formula for the PDF, integrate that over the possible values of x that you might see, and then subtract off the square of the expected value. So subtract off mu squared. That's an alternative formulation for the variance where if you give this a really mathematical treatment, sometimes this is a little bit easier to calculate. But numerically, with Wolfram Alpha or R, it's actually going to be easiest just to stick with the original definition, the expected value of x minus mu squared. Now, there are some mathematical properties of the expected value and the variance that we should be familiar with. Because if we do have a random variable, say capital X, and we do want to ask questions like, hey, well, what's the expected value of 3 times x? Or if I find two random variables, x and y, what's the expected value of their sum? There are a few rules that can allow us to very quickly get to those answers without having to do much extra work. So first of all, if I were to ask what's the expected value of x just scaled up by some factor b, so let's say we're translating from dollars into yen, there's just a simple formula that relates the two. I need to take dollars and multiply it by some amount. Well, I can do that very easily. If I want to know the expected value in yen, and I know the expected value in dollars, e of x, all I have to do is multiply that conversion factor times the expected value in dollars. So in other words, the expected value of b times x, my conversion factor times the amount in dollars, is just that conversion value times the expected value in dollars. Likewise, if I have two different random variables, let's say x and y, and I want to know the expected value of their sum, well, it's just the expected value of x plus the expected value of y. And I can extend that to a much more general case. What if I had the expected value of some constant a plus b times x plus c times y, some sort of weighted sum of those two random variables? Well, expectation is what we refer to as a linear operator. And so what that means is that I can just get the expected value of the sum of a bunch of different things by summing up the component expected values. So the expected value of a plus b times x plus c times y would be the expected value of a plus the expected value of b times x plus the expected value of c times y. The expected value of a constant, is just the value of that constant itself. The expected value of b times x is just b times the expected value of x, and the expected value of c times y is just c times the expected value of y. So getting the expected value of some constant times your random variable, no problem. Getting the expected value of a weighted sum of random variables, no problem at all. But just remember that in general, when we ask the question, hey, what's the expected value of some general function of x, g of x, that in general is not obtained by plugging in the expected value of x into your equation for that function. The expected value of the worth of that steel produced wasn't the expected value of the amount that was produced into our equation that related the amount to the worth. So there are some properties of the variance that you're going to want to be familiar with too. So first of all, if we're dealing with a non-random quantity, let's say just the number a, and I were to ask, well, what's the variance of a? Just by thinking about it, you automatically know that the variance of a constant is going to be 0. It's always the same value. There's no variability to it. And so there's no typical difference between the values we might observe and the average. Those are one and the same every time. So the variance is 0. What if we were taking our random variable x and then scaling it up or down by a factor b? So x is the amount in dollars, and we're interested in the amount in yen. We can get from dollars to yen just by multiplying by a conversion factor b. And when we think of variances, it's actually very easy to go between one and the other. I know the variance in dollars. I can get the variance in yen pretty easily. I take the variance in dollars and multiply it by the square of that conversion factor. So the variance of b times x is actually b squared times the variance of x. I can take a constant out kind of in front of that variance operator as long as I promise to square it. And that makes sense because if I think really in terms of standard deviations, which I'm very comfortable doing, the standard deviation of the amount in dollars, if I just scale that up by b, should give me the standard deviation in yen. And so since the variance is the square of the standard deviation, that's why that b gets squared when you pull it out of that variance operator. Now, what happens if we have, let's say, the variance of some sort of function of our random variable? Well, bad news. It's actually really difficult to calculate. We're not going to worry about doing that in this class, but as we can see, the formula that tells us the variance of some function of our random variable is pretty involved in terms of computation. So when we talked about, okay, the expected worth of the amount of steel being produced, we were able to get the expected value of that worth pretty easily. But if we wanted to know the variance or standard deviation of that worth, well, guess what? There's actually a lot of additional calculus that we need to do, a lot of additional expected values that we have to calculate. And here's going to be the rub. So when we had a weighted sum of two different random variables, and we had the question, well, what's the expected value of that weighted sum? That was fairly easy to do. We just take the weight assigned to the random variable x, multiply it by the expected value of x, and then add that to the weight assigned to y times the expected value of y. There's no similar formula for how we get the variance of a weighted sum of two different random variables because it actually depends a bit on how related they are. It depends on their correlation. So we'll revisit this when we talk about joint distributions of two or more random variables and how we talk about how strong of an association exists between the two. But for now, just keep in mind that if you have some quantity that you're interested in, that's a weighted sum of two different random variables, easy to get the expected value of that, but it's very difficult to get the variance or the standard deviation because you have to account for how strongly related those quantities are. All right, in a more mathematical class that was studying probability, you would have a big, long discussion about the moments of a random variable. The expected value is actually just the first moment of the probability distribution. The standard deviation, or variance, is related to the second moment of a probability distribution. In general, we say that the nth moment of a probability distribution is just the expected value of a very special function. Take x raised to the nth power, get the expected value of that function by integrating x to the n times your formula for the PDF, and that is known as the nth moment of your probability distribution. So why is this useful? Well, in math, it's kind of useful for doing some proofs. We don't have to worry about it all that much, but we really can't have a discussion about probability distributions without bringing up the moment generating function. Because it turns out you can get values for the moments of the probability distribution by just calculating the expected value of a particular function and then taking a bunch of derivatives. So the very special function that we want to look at is the function e raised to the t times x power. If we get the expected value of this function, this is what's known as the moment generating function because it generates moments. How does it do so? Well, after you do that integration, you're going to get a function that involves the variable t. And so here's kind of the cute thing that you can do. If you take the first derivative of that moment generating function and then plug in the value of t equal to 0, that gives you the first moment. If you take the second derivative of the moment generating function, evaluate that at t equal to 0, throw in t equal to 0 there, you get the second moment. The third derivative, plug in t equal to 0, the third moment, etc. So why is this at all interesting? Well, it's used in some mathematical proofs. We'll mention it in passing when we talk about the central limit theorem, but this is really a big friend to mathematicians, not so much to business analytics practitioners. This doesn't really tell us anything definitive or interesting about a probability distribution just by itself. Now, in that earlier example, we calculated the expected value or the typical value of the demand probability distribution, which was bimodal. And we said, it's probably not a smart idea to summarize this distribution with a single number because there's two peaks, and we should probably summarize each peak separately. And so we have a name for that. The mode of a distribution is where that distribution reaches a local maximum. So if I go a little bit to the left, a little bit to the right, higher, lower values, I don't have a higher probability. I have a mode in that distribution at that value of x. So that bimodal demand distribution has a mode right at about 0.75 and another mode right up a little bit above 2.6. So very often, when we do summarize a probability distribution, we might actually just want to talk about where is the peak of that probability distribution. Average value is a good measure for measuring the typical value, but what if we just want to know, well, what's the most likely sort of value? Where's the peak? Well, if we think about it, we can use calculus, specifically derivatives, to figure out where the modes of a distribution are going to be. Now, the derivative of the PDF is going to be the slope of the tangent line to the PDF at that value of x. And so if we focus in on the shape of the distribution, we can see that a peak happens where the derivative, or the slope of that tangent line, is equal to 0. Momentarily, at least, that tangent line is completely horizontal with a slope of 0. So we have a method for calculating where the modes of the distribution are. We can look at the plot of the distribution itself. We can look to see, okay, where does it peak? That's going to correspond to where the first derivative of that PDF is going to be equal to 0, where the slope of that tangent line is 0, because the tangent line is going to be horizontal. So let's try to figure out what the mode of this PDF is. 0.04 times x times e to the minus 0.2x. I'm going to first do this in R, because R has a very powerful function called optimize, which actually will tell us immediately where the peaks are for any particular distribution we have in mind. So how does this work? Let's head on over to R and transcribe our PDF. We're always going to make sure that we're dealing with a valid PDF just by ensuring that it integrates to 1. So let's take 0.04 times x times e raised to the minus 2 times x power, and let's integrate it over the possible values of x we might see, which is from 0 up to infinity. So am I dealing with a valid PDF? Absolutely. Great. So where am I going to find the mode, the peak of this distribution? Well, we're going to use the function optimize. With a z, if you're British, you can use the s. And so for our first argument of optimize, what we're going to do is to just copy-paste what the function is that we're trying to find the peak of. Function x, and then our formula for the PDF. And then what R would like to know is, okay, well, where should I search for this peak? So if we go back and look at the shape of our probability distribution, we see that it's happening somewhere between 4 and 6. Let's go ahead and give it a bigger range of 0 to 10 here. It just needs a range to look over. And so we'll have that be the interval argument. We'll say to search from 0 to 10. And we're going to tell it, hey, let's try to find the maximum. Maximum equals to true. So when I run this, I get 2 bits of output. I get the $maximum component, and I get the $objective component. I'm going to look at the $maximum component because the $objective actually just turns out to be the height of the curve at the peak here. I don't really care what the height of that curve is. The height of a PDF doesn't tell me anything about the probability of a particular value. I just want to know what the value of x is where I find that peak. So it told me it was right at about 5, and that looks pretty reasonable. Tracing up here, it looks like 5 is where that peak occurs. All right, well, how would I do this in Wolfram Alpha? I'm going to go and borrow my equation and head on over to Wolfram Alpha. Go ahead and just run that in the input box so I can get a plot of it. Wolfram Alpha says, ooh, this is a crazy function. So let's actually say from x equals 0 to, let's say, 10. The only valid values of x in this case are from 0 on upwards, and so we recover that same plot that we saw on the slide. I know that the peak is at 5 in this case, and so how can we get this out of Wolfram Alpha? Well, let's do this the calculus way. We know that the peak is going to be where the derivative of the formula for the PDF is equal to 0. So let's ask for the derivative of our PDF with respect to x. So it'll go through and it'll come up with a formula for what the derivative actually is. So throw in a particular value of x that'll tell you what the slope of the tangent line is to the PDF at that value of x. But what I'd really like to know is, okay, well, where is the slope of the tangent line equal to 0? Where is the derivative equal to 0? So what we can do is we can put this inside a big pair of parentheses, and we can ask Wolfram Alpha to solve this. So solve whatever expression emerges from taking that first derivative equals to 0, and we're solving it for x. So solve where that derivative is equal to 0 for x, and boom, Wolfram Alpha says, hey, that actually happens at exactly 5. A little bit better than ours answer, 4.99999, etc., because Wolfram Alpha is able to use some of its tricks to figure out where this happens exactly. So finding where the peaks of a distribution occur, really not so bad. It just boils down to either running optimize in R or actually taking the derivative in Wolfram Alpha and then solving where that derivative is equal to 0. Now, what if we were to do this for our original bimodal demand problem? Here we have two peaks. Well, how can we get the locations of both peaks in R and Wolfram Alpha? All right, let's try it out. We'll use the optimize function in R. So what I'm going to do is, once again, take my equation for the PDF of the probability distribution we're working with, and I'm going to make sure that it integrates to 1, that I didn't do any typos, and it does. So here's the formula for my PDF. I'm going to run optimize and just throw in what the equation for that function was. And then I'm going to say, okay, well, what interval do I want to search? And in this case, I need to do two searches. I know the first peak happens right at around 0.75. The second peak is somewhere close to 2.5. So I'm going to run two searches separately. For this first search, I'm going to say that the interval is equal to from 0 to 2. I know it's really close to 0.75 here, but I'm just going to say search everywhere from 0 to 2. And we get that the mode is at 0.754 here. And then for the second mode, well, I know it happens right at above 2.5 here, but I'm going to say go ahead and search from 2 to 3. Give it a bigger range. It'll do its thing, and it'll find out that that second mode, that second peak, is right at about 2.57. So pretty much what I saw from the plot itself. This happens right at about 0.75. This happens right at about 2.6. We're good to go. All right, now Wolfram Alpha will actually give us all the solutions, but we'll have to actually pick out the solutions that don't matter to us. So let's go ahead and take our function in this case for the PDF, and let's throw it into Wolfram Alpha. We can get a plot of it. Wolfram Alpha will try to choose an intelligent set of limits here. Let's restrict it from x equal to 0 to 3.5 because that's really the possible values of x that we might see from this probability distribution. So we see, our modes pretty easily visually. How do we coax this out of Wolfram Alpha? Well, we can say, let's get the derivative of this function with respect to x. So we'll get a nice long equation that tells us what the derivative is. Throw in a value of x and you get the slope of the tangent line to the PDF at that value of x. But we want to know, well, where's the slope of that tangent line equal to 0? So we'll put our whole command, derivative command in parentheses, and then say to solve whatever expression emerges from here, that expression equal to 0 for x. Find at what values of x that derivative is equal to 0. And Wolfram Alpha is going to be like, I'll do it, and I'm going to give you a whole bunch of additional values, because it turns out that beyond the range from 0 to 3.5, there are a lot of other places where there are peaks. We're restricting ourselves between 0 and 3.5 here, so we just need to do a little bit of extra work to see, well, which ones actually correspond to the peaks that I'm interested in. I know x is between 0 and 3.5, so these peaks that occur at negative values for this function in general, don't care, throw them away. So here's our first peak that actually does meet our condition of being between 0 and 3.5. That's that 0.754 that we saw before. So that's peak number 1. Notice that Wolfram Alpha is spitting out an x of 1.5 as well. And that's weird because we didn't see a peak that was close to 1.5. What does that correspond to? Well, if we look at it, 1.5 is where this function momentarily ends up in a trough before increasing. So if we think of the derivative as the slope of the tangent line to the PDF at that point, at a minimum, the slope of that tangent line is also going to be 0. So Wolfram Alpha is actually outputting both where the peaks are occurring and the troughs are occurring. So we just need to be careful that we're throwing away the ones that we're not interested in. So this 1.5 actually corresponds to a trough, a minimum in that function. That next one, that 2.578, that corresponds to the peak as well. So we found both of those. So how do we know which are peaks, which ones are troughs? Well, we can do some additional calculus to actually figure that out, or we can just use our eyeballs. I highly recommend always just plotting what the shape of your PDF looks like so that you know which of these solutions are going to be valid. If I were to ask what's the variance, I think a banana is going to help. Gotta eat this banana.